specifically the log laws, evaluating logs, and also solving with logs. The next video will look at some functions and some applied situations for logarithms. Now, logarithms, we're going to start off with just a bit of a definition through this way here. So we're asked to find the logs of these functions here. So first thing is, what is a log? Well, a log is, firstly, you have some kind of base. Now, if a log is blank, then it means the base is base 10. And what we're saying here is 10 to the power of something is going to make 100. So can you think of what would be raised to the power of 10? So 10 to the power of something will make 100. Well, we know that 10 to the power of 2 is equal to 100. Now, this is what a log is how many times do I have to times this base by itself to make 100. So if I times 10 to the power, times it by itself twice, then I'm going to make 100. And this is our answer. For the next one here, how many times do I have to times by 10 to make 0.1? So 10 to the power of something makes 0.1. Now in this case here, you may remember, if you've looked at the exponential videos recently, 10 to the negative 1 makes 0.1. Therefore, how many times do I have to raise 10 to make 0.1? I have to raise it -1 times. So the answer here is -1. Now I'm going to show you another way of doing these problems, because we're going to transfer this other method onto this example over here, which I would call a trickier problem. So another way you can express this is you can say log 10, and then let's match this base. So 10 to the power of something makes 100. Now, this here is the answer. If you match these bases, then your answer is just going to be 2. So we can say that the answer in this case is 2. And this matches with this answer over here. Now the reason this may not seem that useful here, but we can start applying that for all of these examples, even trickier ones. Now I'm going to write down the rule for this first. If I have log base a to the x, then the answer is simply the index, just here. So the answer is x. Okay. Now this rule is really handy, and we need to know it both ways. So let's apply this knowledge to the other two examples. So I've got log base 10, you don't have to write the 10 if you don't want, 10 to the -1, so the answer is -1. So just get this -1 coming down here, 2 going there. The last example over here, we're going to do as the same. So I've got log base 10, and then I'm going to express, I'll keep the 4 there. Actually, I prefer to do it this way, so I like to go to a fraction first. Next, let's express as base 10. So this is 10, and then we've got 10 to 1, 2, 3, 4. It's not very exciting, is it? Maybe I was going to have one more 0 in there. Let's just whack one more in just to make it a bit more interesting. Here we go. 0, 0. Oh, and now I can do this. This will be 10 to the power of 5 to the corner. Now I can bring them together. So here's my answer. It's equal to 5 on 4. Okay, apologies for all this stuff up there. So this is us using the definition of a log. 10 to the power of something makes the number we're trying to find. Okay, so that's the way I like to think about these. We're going to move on to some different bases, but the same theory holds. Okay, so give ourselves some space here. Okay, so I'm going to write down a few more examples here with different bases. Log 3, 81, log 4 of 1 on 64, and one of my favorites, log 36 of 6. So in this first one here, we're going to use that same rule just here. So let's just match these bases. Now, like in the previous video for exponentials, we've got to know those powers. 3 to the power of 4 is 81. Therefore, our answer is 4. Okay. Over here, this is log 4, 1 on 4 cubed, which is log 4, 4 to the negative 3. Therefore, the answer is negative 3. Now over here, this is one that people find quite tricky. We have to match the base. 36 to the power of something makes 6. Now, some people get it, some people don't. It's a half, right? 36 to the half. Where does that come from? Well, we know that that's the square root of 36, right? Which is 6. So therefore, our answer is a half. Okay, now using this method, this is obviously going to be a non-calc section, and this is how we can simplify, evaluate logarithms. Okay, now we're going to move into the log laws. The log laws, there's basically 3 main ones, and they're used in some further simplifying and solving situations, so we need to know this really well. So here we go, we've got the log laws. There is nowhere near as many as the index laws. I remember that video there, there's quite a few that came out. The first one, log a m plus log base a n is equal to log a m times n. So if you're adding 2 separate logarithms together, if you want to bring them together, you can take the product of their m and n. Log a m take log a n is equal to log a m divided by n. The last one is log a m to the power of n is equal to n log a m. So we can see in this case, this n moves down here, or if you want to think about it, the m moves up there. So we can switch between them. Now with each one of these log laws, we need to be able to go this way, but also this way, okay? So we need to be able to switch between both forms. There's situations that calls for simplifying, which is going from the left to the right. There's some situations where we need to expand as well, going from the right to the left, okay? So without further ado, let's go into some problems that are pretty typical, okay? And we may have enough space. No, let's do underneath, okay? So we're asked to simplify. Okay, so here's our first one. Second one. And third one. Okay, now I want to talk about what the term simplify means. In logarithms, it usually means express as a single simplified logarithm. Now you may note that we don't have a log written here, we've got something called ln. Okay, so let's go into what the ln means before we simplify these. Now ln, let's go blue, ln is equal to the natural logarithm, and is linked to the e function, which is the natural exponential. Now something that might be very helpful for you is we may consider this function. We can go ln of, let's say, e to the 3 is equal to exactly the same as log e to the 3. So we can see that ln can be interchanged with log base e. So instead of writing log base e all the time, we just use ln. Okay. Now, if we can see also that we can simplify this function, because if we've matched the bases here, e base e and then e to the 3, then the answer is simply going to be 3. So all these log laws and all these rules we've been learning, the log laws are applied to the ln laws. ln is a log, so there's nothing really that special about it, except that e, that number 2.7183, that comes up a lot, and that's why we use it a lot as well. So nothing to be afraid of with these ones. So first step with these for simplifying is I like to express hang on, it's basically the same as the exponentials. So no coefficients at the start, and we want to match the bases, so match the logs. Okay, that's a sort of rule of thumb at the very start. So what I mean by this is we've got a coefficient here and a coefficient here. To bring these two together, we're going to have to get rid of those coefficients. We can add the coefficients back later. So this one here, we can see that 3 ln2 is going to become ln2 cubed y, or you can look at this log law here. We have this 3, it's going to move up to this position here. Okay, then plus ln64 to the half, right? Same rule. Let's simplify these or evaluate the 2 cubed, 8, plus ln of the square root of 64. Obviously, you know the answer, you can just put in ln 8. Right, we're really close. We haven't expressed this as a single simplified logarithm yet. Now we've got ln 8 plus ln 8. You can either express it as 2 ln 8, so there's two ways of doing this. You can call this 2 ln 8, which becomes ln 8 squared, which becomes ln of 64. Or you can go a different way about it, and you can go, well, ln 8 plus ln 8 is ln 8 times 8, which comes from the first rule here, which becomes ln 64. So same way, different ways to get to the same result. Let's move on to this one here. You may notice there's just a number hanging around. Now, if there's a number hanging around, and I'm just going to scroll up, this function here is what we really want to tap into to transfer the number into a log. So first thing, 2 ln 5. That's going to become ln 25. So I'm just going to take my shortcut now. The 2 goes to 5, becomes 25. Then we need to make this 3 go into ln form. So I'm going to go take and then ln e to the 3. Okay, so we're just tapping into that rule. X is equal to ln e to the x. Right, so it's tapping into that rule there. And so if I evaluated this, it would actually just be 3. The reason we're transferring into ln is because we need to get these as the same log with the same base. Next step is we can use our second index rule being the take one. We can divide those terms. So now we have ln 25 on e to the 3. And there's our answer. Let's move on to that last one over here. Okay, 5 log base 4 of 2 plus 2. We do the same thing. 2 to the 5 is 32 plus, and this one here, to make it 2, we need to match that up. So we're thinking log base 4, we're going to match that base, 4 to the 2. So log base 4, 4 to the 2. Let's evaluate that. Okay, and we times them together. Log base 4, 32 times by 16. Now I don't have a calculator, but yeah, that's more or less what you're doing, and you can bring that together by multiplying them. Okay, so there we go. That's our first set of simplifying logarithms, and we're just using all those log laws, as you can see. Okay, Now, I have done a fair bit of solving our log laws, and if you remember those videos we made, I made, sorry, a while back, which was looking at, and if I scroll down, to do 6G, I believe. Yeah, so I did applied situations, I've done solving, right? So there's lots of great questions in there. Please make sure you've done lots of these questions. But yeah, we don't need to go too much into those questions. What we will be doing is doing some changing base, okay, and some solving, converting equations to log form and without log form, okay. So yeah, and what I will do is I go through a few of these changing base ones. These are, personally, I think they're quite fun, but yeah, they take a bit of time. So what I'll be doing is I'll just copy this out and just work through those in this video as well. Okay. So I'll put that pretty far down. I'll put it to the side for the time being and I'll paste it in a bit later. Okay, when we get to it. Okay, so let's move on. We're going to be converting equations now into log and exponential form. Okay, so this is going to be converting from exponential to log equations. It's an important skill, it doesn't come up as much as some other skills, but it still needs to be able to be done. So what we're going to do in this case, the first question is going to be, can you convert these equations to logs? So this is exponentials to logs to start us off. Okay, first equation. And the second equation. Okay, now let's have a look at this first equation. Now this is an exponential form, we want to get to log form. The first thing we can do is just simply take a log of both sides. Now when we're converting from exponential to log form, this probably isn't enough. We need to sort of expand this out as much as we can. So we don't want to make this a single log at all. We want to make it as every variable has its own part, so its own term to it, and every power becomes a coefficient. That's our aims. So I can keep the left-hand side the same, but I can break this apart according to my first log law. So I'm working the other way. If these are timed together, then it stands to reason I can break it apart by expanding like this. And the very last step is I want to express it with no powers, only with coefficients. So I'm going to bring that n down in front of the log b. And that's it. That's all you have to do. We're going to move on to this one now. Do the same thing. I'm going to express this as a fractional. Instead of root k, I'm going to do half, k to the half. Next step, same side. It just stays like that. And I'm just breaking this apart. So these are times together, so a squared plus log b to the 3n. And then we're going to take away log k to the half because it's dividing. Next step, get rid of the powers. And that's it. So there we go, we've converted both of these exponential forms into log forms, log equations. What we're going to do now is go the other way around. So we are going to go from log form into exponential form. So here's some equations we're going to be looking at. And this one here. Okay, now in this one here, the first step is we want to express both sides, left-hand side, right-hand side, as a single log. So let's do that now. So first step, ln r is equal to ln t squared. So we're doing the inverse, where like all the coefficients need to come out. So I'll write here no coefficients as well. They've got to go to powers, right? And then we go take ln q to the half. Cool. Next step is we can now express this as a single log, because these are both ln functions, so they're the same base essentially, log e. So we can go t squared divided by k to the half. We'll change it back into square root. Now what we can do, something pretty cool, is we can take e to the both sides. So essentially we're taking e to the both sides, much like taking a log of both sides, and e to the ln r and e to the ln's, they are essentially working against each other. So e to the ln r, your answer simply just becomes r. So r is equal to, and the e and the ln are essentially cancelling. So you've got t squared on root q. And that there is your exponential version. Now what we can always do to practice and see if you have got the right answer is, now that you've got an exponential form, see if you can work it back into log form, right? And if it does the same thing, that's fine. Just the only thing is they've used ln, so just make sure you take an ln of both sides, otherwise you'll be a bit confused. Yeah. Let's have a crack at the one on the right hand side. So first step, we want to bring everything together. So we want to get rid of those coefficients as well. So let's do that first. Next, we want to bring everything together like that. Then we're going to take, in this case, is base 10. So we're doing 10 to the power of both sides. That cancels out those logs. So you're left with e is equal to mc squared. Yes, that's right. All right. So there we go. We've done those there. What we're going to be looking at next is what was it? We've done solving. Just on the tip of my tongue. Oh yeah, that's right, changing base. Okay, so I'm going to get that sheet now and just drag it down. Okay, and this is from the OneNote from your booklet as well. And we've got some rules there. It's pretty handy for solving. There we go, and I'm just going to make that a bit bigger. Okay, so we're looking at changing base first. And I just want to go through what changing base means, and then we can go through this sheet. So changing base. Now, usually there's a bit of work in these, but they're quite satisfying when you get them. I'll show you how changing base works. So I actually quite like to show the ln function. So you might have a function, it's like y is equal to e to the x, right? Now, we know that we can get x by itself if we take the ln of both sides, right? So what we're going to do is take an ln of both sides. All right. Oh, sorry, I'm getting ahead of myself. Take a log of both sides. Like that. Next step is we want to get x by itself here. So we're trying to make x a subject. Now, you see the x is a power. What's great about logs is it makes a power go to a numerator. So we can bring that there. X log e log y. Next step is we want to get x by itself, so we can divide both sides by log e. And I'm going to switch these at the same time. Okay. Now, what's cool here is that this e can go here and become the base, okay, of this function. And this is called the changing base rule. So we can write our final answer, log ey, which is also known as lny. So it's pretty cool. So we've just shown something here, a bit of a shortcut now we can say, is that y is equal to e to the x can also be expressed as x is equal to lny. Another handy equation that you might want to use as well, I'll write it in green over here, is you've just got y is equal to a to the x, so this isn't an E1, it's equal to x is equal to ln y. So we're swapping the inputs and the outputs, that's sort of what's happening. So what's the changing base rule? It looks like this, and log and a of b is equal to log c b of log c a. Okay, now this seems like a strange rule in a way. We're going to use it a fair bit soon, so don't worry. What's happening here is if I want to express this log a to the b, I can re-express it like this. So just some examples we could throw at this. 4 of 6 is equal to log 6 on log 4. Okay, so I can break the 4, bring it down here and make it divided by log 4. Okay, so log 6 divided by log 4 is log base 4 of 6. Okay, so with this in mind, this is a really powerful technique for matching bases for logs if they've got a common power to them. So looking down below, we can do some what I reckon some pretty cool examples. So in this case here, this is a simple, well, not simple, but we've solved these before and in previous videos, but tell you what, I will go through this one just to warm us up. First thing, write all terms in log form with the same base. 4, 4, 4, already done. 2, simplify all logs so there's no coefficients. Yeah, it's all done. Number 3, simplify all logs so that there is only one log term ls left-hand side and right-hand side of the equation. We haven't done that there. So let's have a crack at this. We're going to have log base 4, 64 times 1 on 16 is equal to log base 4 x plus 1. We've done that now. We can bring these together. Log base 4, and this becomes simply 4 is equal to log base 4 x plus 1, right? Now the next part, it says solve the equation inside both log terms. Now that we've matched these log 4s, it stands to reason that the insides must also be equal. So let's pull out that. 4 is equal to x plus 1, therefore x is equal to 3. These are quite satisfying, right? So there's plenty of these to practice, but that's just the premise of these. Now you may note that the first step says write all terms in log form with the same base. Now this is where the changing log rule comes into play. Let's go down and see if we can find one. So I haven't actually copied those examples. Well, that's not that useful. So let's just quickly go back and pick up a changing base question. Oh, right, that was 6e. Okay. Right, well, I have been through these already, but I could go through them a little bit more. But what I'll do is I'll just copy out this example here as well. Okay, apologies. Bit more. There we go. Okay, cool. So what I'll do is I'll actually just go through these ones because they're all pretty good. It's pretty good to do a recap here. So first thing, we need to express everything with no coefficients. So this becomes log x squared, take log 4 is equal to, and we want to match this to in terms of log. This is all log base 10 squared. Next step, let's bring this as 1 log. Okay, now I really like this question and I'll show you why soon. We can now equate the insides. X is equal to plus and minus, and we're taking a square root of 400. So x is equal to positive 400 and negative 400. Whoa, what am I doing? Negative 20 and positive 20. Now, we actually have not finished now. In logland, we know that we can't have a log value. So I'll show you what I mean. Let's say we have, can you find the log base 10 of negative 100? All right, Really tempting to say -2 here, right? Thing is, we know that 10 to the power of -2 is 1 on 100. So it actually can't be done. You can't have a negative log. You can't have a negative value here. So therefore, we can discount one of these solutions. Now, I actually don't mind if you actually write out both solutions. You're showing the marker what you're doing, but then you discount the negative solution. Okay, let's move on to this last one here. Log base 3, x, log base 3, x plus 2, log base 3, 12. So they all have the same base. Let's bring them together. Equate the insides. Expand. And we see it's quadratic, so we may as well bring it to both sides. So I'm going to use Null Factor Law now. And this one will be, what is it? 6 and 2, 4 and 3. Oof, not sure. What do we got here? So that's going to be x plus 2 take 12 plus 6 take 2. I'm not really sure here, so we might have to do a bit of complete the square. And then solve. So therefore, x is going to be either equal to -1 plus or minus root 13. Now we know we can't take off the root 13 solution. Therefore, there's only one solution, root 13. Okay, that's a bit of a trickier one, but yeah, we're just using the same principles. Now we're going to move on to our changing base. Okay, now we've already introduced it. So yeah, let's just get straight into it. So these ones here, we're using the same steps as the log equations from 6a, but we're going to use the change base rule. So here we have a log base 5 and a log base 25. We want to express this in the same base. Now, something cool here is that we can see this is 5, this is 25. We can basically convert this log base 25 to log base 5 using the changing base rule. Okay, so here we go. Now, I'm just going to be operating here for a long time, so I'm just not going to bother bringing this down. Now you can see I've got log 100 of log 25. That's exactly the same as this. Now I can do something very clever here. I can express this as 5 squared, right? Now why is it useful? Well, remember our third log law. I can bring the 2 to the front of log 5. And then you may notice that I've got a log, so if you cover up this 2, I have log 100 on log 5. What's amazing about that is that's exactly the same as saying 1/2 log base 5 100. Wow. What have we done? We've just converted it to base 5. Remember the first step of solving equations? We had to write all terms in log form with the same base. We've just using the changing base rule to do that. So let's bring everything else down now. We finally can actually start working with those. Okay, now this 1 we want to convert into log form as well. The base is 5, so let's go log base 5, 5 to the 1. Now we can get rid of our coefficients. Now I hope that made sense. I simply just went the square root of 100. So it's going to be to the power of 1/2, which is 10. And we can bring these together. Now we can equate the insides. Plus 20, so 25. So x is equal to 2.5. Wow, there's a fair bit in that, but that's how we use our changing base rule. Okay, now I'm going to end the video here. We've looked at a fair bit in this video. We looked at a recap of log base 10s and what the definition is, how to evaluate logs using this idea. considering it's 10 to the power of something makes this term here. That's a really good way of thinking about logs, and how to do trickier ones using that rule. We did a different base instead of 10, so 3, 4, 36. We had a look at the log laws and how to use these log laws to simplify expressions, and a few tips along the way. We'll learn about the natural logarithm and the natural exponential function and how they work, very similar to logs. And then we worked on converting exponential equations into logs, and then logarithmic equations into exponentials. And then we also did the changing base rule, which from my opinion there's a fair bit of work on it, but they're quite satisfying when you do it. We also had a bit of a recap of our log equations. I know this is actually 6E, and the other questions are from 6G. So the 6G ones are quite even more challenging, but use the same principles that we've worked on here. I hope this video is useful. We're going to be looking at log functions and log applications in the next video. Thank you.